Welcome to the deep dive. Today we're zeroing in on NVIDIA's fresh release, the Llama-Nemotron series.
That's right.
We're talking the Nano 8B, the Super 49B, and the big one, the Ultra 253B parameter models.
And what's really grabbing attention, I think, is how these open models are built for strong reasoning, but also, crucially, for high inference efficiency.
Exactly. And they have this key innovation, this dynamic reasoning toggle.
Ah, yes, that's a really neat feature. It lets users, switch between standard chat and a more detailed step-by-step reasoning output on the fly.
Right, without needing totally separate models. It's quite elegant.
It is.
So for this deep dive, we want to go beyond just benchmark scores. We really aim to explore the academic thinking, the innovative steps in their development that led to these capabilities.
Yeah, understanding the core science, the fundamental advancements, that's the goal.
Our mission is to really unpack those innovations behind Llama-Nemotron's architecture, its training. By getting a handle on these academic contributions, you'll get a much deeper feel for, the cutting edge of building these kinds of AI systems.
Precisely. It's about the how and why behind the performance.
Okay, let's dive right in. A huge piece of this is efficiency. How did they get these models, especially the larger ones, to run so efficiently? The paper talks about neural architecture search, NAS, using something called the puzzle framework.
Right, NAS.
For our listeners maybe not deep in the weeds on this, what exactly is NAS searching for?
Good question. So fundamentally, NAS is about automatically finding the best, or at least a very good neural network structure for a specific job, and importantly, specific hardware.
Okay.
Puzzle's twist is how it searches. Instead of looking at every possible architecture, which is astronomical, it does this blockwise local distillation.
Blockwise meaning?
Think of a transformer model as being built from repeating blocks. Puzzle focuses on optimizing each type of block individually. It creates a whole library of alternative, more efficient versions of these standard transformer blocks.
Okay, so it's like having a toolbox with different versions of the same tool, some faster, some using less power. What are the trade-offs with these alternative blocks?
Exactly like that. Some alternatives might be much faster computationally or use less memory. They mention things like removing the attention mechanism in some blocks.
Whoa, removing attention. That sounds drastic.
It can be, yeah. It definitely cuts compute and the memory needed for the KV cache, which is a big bottleneck.
Right.
They also talked about changing the dimensions of the feed-forward network, the FFN part, essentially compressing it. But, as you'd expect, making blocks more efficient like this can sometimes slightly reduce the model's output quality. It's always a trade-off.
Okay, that makes sense. So you have this library of efficient but potentially slightly less capable blocks. How does Puzzle pick the right combination for the final model, especially considering hardware limits?
This is where it gets really technically interesting, I think. They use a technique from mathematical optimization called mixed integer programming, or MIP.
MIP, okay.
Essentially, Puzzle feeds the hardware constraints like max latency allowed, memory budget, target throughput into this MIP solver. The solver then looks at the library of efficient block variants and figures out the optimal combination of blocks to build the most efficient overall model while staying within those hardware limits.
Wow, so it's not just shrinking the model, it's intelligently sculpting it for specific hardware. That feels like a really core academic insight there.
Absolutely. It's highly targeted optimization, very rigorous.
Now, for the big one, LN Ultra, they added another layer of optimization called FFN Fusion. What was the idea behind that?
Right, FFN Fusion. This builds on what Puzzle did. See, after Puzzle optimizes the blocks, sometimes by removing attention layers, you might end up with several feed-forward network blocks, FFNs, right next to each other in the sequence.
Okay, I can see how that might happen.
FFN Fusion spots these consecutive FFNs and merges them. It combines several Thalwer FFNs into fewer but wider ones.
And the benefit is?
Speed. It reduces the sequential depth of the network. Fewer steps means faster processing, especially important on multi-GPU systems where passing data between layers takes time. Think of it as consolidating steps on an assembly line.
Got it. Streamlining the flow. So these architectural changes, Puzzle and FFN Fusion, they led to some pretty big efficiency wins, didn't they? Can you give us a sense of the numbers?
Oh yeah, definitely. For LN Super, the 49B model, they optimized it for a single H100 GPU.
Okay.
And they reported a 5x throughput speedup compared to Llama 3.370B instruct in certain scenarios. Even against an optimized multi-GPU Llama 3.370B, LN Super was still over 2x faster.
That's impressive for a model that size on one GPU.
It is. And it's tuned to handle about 300,000 cache tokens using FP8 precision, which is a very compact format.
And the massive LN Ultra, the 253B parameter 1 running on 8 H100s.
For Ultra, the focus shifted more towards latency, how quickly you get a response. After applying FFN Fusion, they saw a 1.71x latency improvement compared to the huge Llama 3.1405B model.
Wow.
And it's built for incredibly long context, supporting up to 3 million cache tokens in FP8 or 600K in the more standard BF16. Their figure 4 really shows it off higher accuracy on a tough reasoning benchmark and better throughput than models like DeepSeek R1 and Llama-3.1405B.
Okay, so the efficiency story is clear and really quite compelling, but efficiency isn't everything. Llama-Nemotron is also about reasoning. The development didn't stop after the architecture tweaks, right?
Not at all. That's crucial. NAS gets you efficiency, but like we said, maybe at a slight quality cost. So the next big phase was post-stance training. This involved two main things, knowledge distillation and continued pre-training.
All right, let's unpack knowledge distillation first. How did that fit in after the LN Ultra optimization?
Okay, so knowledge distillation, the basic idea is you have a smaller student model learn from a bigger, more capable teacher. Here, LN Super and LN Ultra were the students.
Right.
They were trained on this special data set, the distillation mix 40 billion tokens for Super, 65 billion for Ultra. The main goal was really to recover any reasoning ability or general knowledge that might have been slightly diminished by swapping in those more efficient blocks during NAS.
So making sure the optimized parts still worked well together and retained the core smarts.
Exactly. Ensuring harmony and recovering that quality baseline.
And then, specifically for LN Ultra, they added continued pre-training on top of that. Why?
Yes. After distillation, LN Ultra got another big dose of training 88 billion tokens from their high-quality Nemotron H Phase 4 dataset.
Okay.
And what's really significant here, academically speaking, is that this extra pre-training pushed LN Ultra to actually surpass its giant reference model, Llama 3.1405B, on key benchmarks. And this was before any task-specific fine-tuning.
Really? Before fine-tuning?
Yeah, Table 1 in the paper shows this. It really highlights how a smartly designed, efficient architecture, when fed enough high-quality data after optimization, can punch well above its weight, so to speak.
So architecture sets the stage, post-training builds the capability. Now, to get that specific complex reasoning, especially the detailed thinking on mode, that required special data, didn't it? This seems like a huge part of the innovation.
Oh, absolutely massive. A really core piece of their contribution was creating extremely high-quality synthetic data tailored for reasoning.
Synthetic data, okay.
They designed it specifically to teach both the step-by-step detailed thinking, on mode, and how to give a direct answer, off mode. The focus was heavily on math, code, and science domains that really test reasoning.
Why the emphasis on synthetic?
Because raw data often doesn't have the explicit reasoning steps needed. For complex reasoning, you need data that shows the thinking process. Meticulously crafted, high-signal data that often means generating it synthetically.
Let's get into the specifics. The math data pipeline sounds intense, starting with art of problem-solving forums.
But they were very selective, not just scraping everything. They targeted advanced topics, filtered out middle school stuff, then did careful extraction, classification.
Classification.
Yeah, removing problems like proofs or multiple choice that weren't ideal for training the kind of chain of thought reasoning they wanted, then answer extraction, and crucially, benchmark decontamination.
Decontamination, making sure they aren't accidentally training on the test questions.
Precisely. They used other LLMs to check for overlap with known math benchmarks. Very important for trustworthy evaluation later.
And they didn't just use the problems, they generated solutions too.
Yes. Using strong models like DeepSeek R1 and QN 2.5 math, they generated multiple solutions per problem, and then, get this, used another LLM to check if the generated solutions were actually logically equivalent to the known correct answer.
Wow, that's layers of verification. Very rigorous.
It really is. It ensures the quality of the reasoning traces the model learns from.
Okay, shifting to code? Similar level of rigor there.
Sounds like they focused on competitive programming data. Very similar philosophy. They pulled challenging problems from places like Code Contest, Codeforces, APPS, did thorough deduplication, and again, super stringent contamination checks.
How'd they check for contamination in code?
Both mathematically, using cosine similarity on code embeddings, and by using strong LLMs like Llama 3.370B as judges to spot similarities to benchmark problems. They found less than 0.3% overlap, which is remarkably low.
That's tiny. And how did they get the reasoning steps for these code problems, the think tags?
They used DeepSeek R1 again, but explicitly prompted it to output its thought process within those think tags. This structure is key for teaching the model how to generate that explicit reasoning trace when asked.
Right, so the data format directly supports the desired output format.
Exactly. And then extensive post-processing. Verifying the reasoning trace made sense, extracting the final code, validating syntax with tools like TreeSitter. They also found that more data helped up to around 736,000 high-quality examples improved performance. Scale matters, but quality is paramount.
That focus on explicit, verifiable reasoning in the training data really seems like a core academic takeaway here. What about the science data pipeline?
A blend there. They curated open-ended and multiple-choice questions from places like Stack Overflow, but also did a lot of synthetic generation.
How did they generate science questions?
It was quite sophisticated. They used one model, Nemotron 4 340B, to define topics, subtopics, difficulty levels, and then another QN 2.5 to actually write the questions based on those specs. They also augmented it using methods from Open Math Instruct 2.
Interesting.
And again, decontamination against science benchmarks was key. For generating solutions, they used DeepSeek R1, and for questions without a single ground truth, they used a majority vote from multiple generated solutions.
It's just an incredible amount of careful work crafting this reasoning data set across different domains. And they also needed data for the reasoning off mode, right?
Yes, absolutely. Teaching the model when to be detailed, when to be concise, was critical for that dynamic toggle feature.
How'd they create that data?
A mix of synthetic prompts and real-world ones. They got responses from DeepSeek R1 and filtered them for quality using a reward model. Crucially, they also created paired examples, the same prompt, answered with detailed reasoning and without it, using different Llama instruction models.
Ah, direct comparison training.
Exactly. And for general chat quality, they used a whole feedback edit select system involving multiple models to generate really high-quality, helpful responses.
Looking at Table 2, the data distribution is heavily skewed towards math and code, but there's still a lot of reasoning off data too.
Yeah, that distribution really reflects their goal. Build strong logical reasoning, but also ensure the model is a capable, controllable assistant that knows when not to dump a huge reasoning trace.
Okay, so you have this amazing data set. The next step is getting the model to learn from it. That's supervised fine-tuning, SFT.
Correct. SFT is where the model actually learns to replicate those reasoning patterns and respond to the detailed thinking on-off cues. They used a standard loss function, cross-entropy, but interestingly noted that higher learning rates seemed necessary to properly learn from the very long reasoning sequences.
Longer sequences need a bigger push, maybe.
Seems like it. And they tailored the SFT strategy depending on the model size.
How so?
For L and Nano, the smallest, it was a three-stage process. First, just reasoning data, then mixed reasoning on reasoning, then finally chat, instruction following, tool use data.
Okay.
LN Super just got one pass, one epoch, over the full mixed data set.
Simpler.
And for LN Ultra, the giant, they used tricks like sequence packing for efficiency and a careful learning rate schedule linear warn-up, then cosine decay to keep the training stable. They even mentioned having to restart training once due to instability. Training models this large is tricky.
Definitely sounds like it requires careful handling. Now, SFT teaches the model to imitate the data, but to go beyond the data, maybe even surpass the teacher models used to create it, they turn to reinforcement learning, right?
That's exactly the motivation. RL, specifically using their GRPO algorithm, was applied only to LN Ultra. The explicit goal was to push its reasoning capabilities beyond even DeepSeek R1, which was used to generate much of the reasoning data.
How do you reward a model for better reasoning during RL?
Good question. They used two main reward signals. First, an accuracy reward. They had another powerful model, Llama 3.370B Instruct, automatically judge if LN Ultra's answer to a problem was correct.
Okay, an AI judge.
Second, a format reward. This simply checked if the model correctly used the think tags when it was supposed to be in detailed thinking on mode. It rewards following the instructed format.
Makes sense. And I read they used a curriculum learning strategy. Gradually harder problems.
Yes, that was a key finding for them. They found that starting RL with easier prompts and gradually increasing the difficulty helped stabilize the training and led to much better final reasoning accuracy. They actually used LN Super's success rate on prompts to gauge difficulty and dynamically adjusted the mix in each batch. Figure 6 shows this really helped.
That's clever. And the scale of this RL training, 140,000 H100 hours, that's immense. What kind of tech setup does that need?
It's staggering, yeah. It required serious infrastructure engineering. They ran their Numo Aligner toolkit for GPO alongside VLLM for generation and Megatron LM for training, all co-located on massive clusters, think 72 servers, each with 8 H100s.
Wow.
Managing memory across GPUs, CPUs, shared memory was a huge challenge. They needed complex parallelization strategies, tensor parallelism, pipeline parallelism, data parallelism, all working together. And they even implemented FP8 inference generation during the RL loop itself, which gave them a 1.8x speedup over BF16. Just incredible engineering optimization.
It really shows that pushing the state of the art isn't just about algorithms, it's also about hardcore systems engineering.
Absolutely. You can't do one without the other at this scale.
Okay, so after all that intense reasoning-focused RL, did they do anything else to polish the models? Maybe for general helpfulness or instruction following?
They did. Shorter runs of reinforcement learning for preference optimization, or RLPO.
RLPO.
For LN Super and LN Ultra, they used methods like RLHO specifically to boost performance on instruction following benchmarks like IFEVL.
Okay.
And then for general chat quality and helpfulness, what's often called RLHF, reinforcement learning from human feedback, they use their own reward model, Llama-3.1-Nemotron 70B reward, trained on the Help Steer 2 dataset. They used online RPO for the bigger models, offline for nano.
And did that help?
Yes, and interestingly, improving the general chat abilities seemed to also lift performance on other unrelated benchmarks too. LN Super got a really strong score on Arena Hard, which measures conversational ability against tough prompts.
So it seems like making it a better chat bot also made it better at other things.
It seems that way, yeah. Perhaps better instruction following or coherence carries over.
What a journey from architecture search through data synthesis, SFT, massive RL for reasoning, then RL for preferences. A truly comprehensive approach. Now, the payoff. How did they actually perform on the benchmarks?
Right, the evaluation. They tested on a wide range of benchmarks. For reasoning, AMI GPQA Diamond Live Code Bench MATH 500. For non-reasoning, IFEVL for instructions, BFCL for function calls, Arena Hard for chat.
And they use consistent settings.
Yes, 32K context, specific generation settings for reasoning on versus off, reporting pass at 1 accuracy typically.
So what were the highlights? How did LN Ultra stack up?
LN Ultra performed exceptionally well. It matched or beat essentially all other open weight models on both reasoning and non-reasoning tasks at the time of the paper. Its state-of-the-art open performance on GPQA Diamond was a direct result of that big RL push. And crucially, it was more efficient than DeepSeek R1.
So top-tier reasoning and efficiency. What about LN Super?
Very competitive in its class. It matched Llama 3.370B's reasoning when the toggle was off and beat DeepSeek R1 distilled when the toggle was on. Showed a good balance between instruction following and chat. Even LN Nano showed surprisingly decent reasoning for its small size, validating their SFT approach.
That's really impressive across the board. And they didn't stop there. They also tested how well these models could act as judges of other AI outputs using Judge Bench.
Yeah, that was another interesting angle, evaluating the evaluator.
How did they do?
Remarkably well. All the Llama-Nemotron models outperformed many well-known proprietary and open models on this task. LN Ultra came out as the best open source model on Judge Bench.
What does that signify, being good at judging?
It suggests really strong generalization. The model understands nuances of quality and correctness beyond just the specific tasks it was trained on. It has perhaps a more robust internal model of what constitutes a good response. Even LN Super was very strong here.
This whole deep dive into Llama-Nemotron's development, it really paints a picture of intense academic rigor meeting cutting-edge engineering.
Absolutely. You see the sophisticated NAS with puzzle and FFN fusion driving efficiency. You see the incredibly detailed, innovative synthetic data pipelines for reasoning, strategic SFT. Then that massive, carefully orchestrated RL phase with the curriculum learning. It's really a showcase.
And the openness is key too, right? Releasing the models, the data set, the training code.
That's a huge contribution. It lets the whole research community build on this work, scrutinize it, improve it. It really pushes the entire field forward.
Definitely. So as we wrap up, thinking about these advancements, particularly in training efficient and highly capable reasoning models, it really makes you wonder, doesn't it? What new kinds of applications, maybe more complex agentic systems, could this enable?
That's the big question, isn't it? Faster, smarter reasoning opens up a lot of possibilities.
We encourage you, the listener, to check out the released models and papers, think about the implications, what doors does this kind of progress open, and importantly, what ethical considerations need to guide where we go next.
Food for thought.
Thanks for exploring the depths with us today.